And here we go. So on Monday, we just talked about that whole idea of a number having two parts and the count and the name, and we looked at the different rules for adding and multiplication. Let's take a look now at what does that mean for operations. Now I realize you guys have all been adding, subtracting, multiplying, and dividing since about the first grade. But I want to go through today not necessarily how we do it, but why we do things the way you do. So we're going to start out with addition. And really the key behind how we do everything that connects with what we talked about on Monday is the idea of place value. Place value is a very simple but extremely powerful tool. We start at the decimal point and we work our way back to the left. Of course, it's the ones, the tens, and the hundreds. And those same place values are repeated over and over again. We now have the ones in the thousands group, the tens in the thousands group, and the hundreds. And of course, that second set of three makes up the thousands group. Then we have the ones, the tens, and the hundreds in the millions group, and so on. Going the other way from the decimal point, of course, we have our decimal places. We have the tenths, the 1/10ths, the 1/100ths, 1/1000ths, and again, going on that way. When we look at numbers, the number that we see as 438 is just an abbreviation. The rest of it is implied in that abbreviation, but the full form of that number, 438, is 4 hundreds and 3 tens and 8 ones. And with it written in that form, and looking back at what we talked about on Monday, the reason we do all of our operations the way we do is more apparent. For example, one of the big things we talked about on Monday is that when we add or subtract, you must have the same name. We can only combine things with the same name. Well, as we look at this here, in the number in its full form or expanded form, we can see that each digit of a number has a count and a name. So if I go to add 347 plus 251, if I write those out in their full form, 300s plus 4 tens plus 7 ones, and 200s plus 5 tens and 1 1, we said you can only combine things that have the same name. Way back when you first learned how to do multiple digit addition, you were taught you have to line up the columns. Well, that's because you can only combine tens with other tens, and hundreds with other hundreds, and ones with other ones when we add or subtract. So once those columns are lined up, all we're doing is combining. 3 and 2 makes 5 hundreds, 4 and 5 makes 9 tens, and 7 and 1 makes 8 ones. You get 598. Now some of you might be looking at that thinking, he did it backwards. I started on the left and went to the right. We've been taught to start on the right and work our way back to the left because you might have to carry. No problems like this. 358 plus 269. We've been taught to start on the right and work our way back to the left because 8 plus 9 is 17, so it's 7, carry the 1. 1 and 5 is 6, plus 6 is 12, so 2 carry the 1. 1 and 3 is 4, plus 2 is 6. Believe it or not, that's not the only way to add numbers. That process of carrying is actually relatively new, just developed in the last 200 years. Before that was developed, and again, you don't have to write this down because I'll never test you on this, but it's just a little bit of math history. Addition was done left to right, just like I did it. And if we had to carry, it was done like this. 3 plus 2 is 5. 5 plus 6 is 11, so 1 carry the 1. 8 plus 9 is 17, so 7 carry the 1. 627. So you get the same answer, just a little bit more room. The main reason I show you that is not to change how you do addition. I realize that most of you are going to do it this way. In fact, many of you are probably going to pull out the calculator when you get to 3-digit addition. But I wanted to make the point that there is more than one way to add numbers. There are several different processes for everything we do. There isn't just one right way to do it. Now, just a little warning on our first unit test, there will be the first half of the test you won't be allowed to use your calculator on, because in the medical fields there's a lot of calculations you have to be able to do quickly by hand. So there will be a section on that will be no calculator. So just to give you a little forewarning. Subtraction, of course, is the same way. You line up the columns because you can only subtract item numbers that have the same name or the same place value. Multiplication then. If I have something like 23 times 31, when we multiply, we don't need the same name. Now I'm going to write this one out in long form as well. 2 10s and 3 1s. This will be 3 10s and 1 1. And as we said, when we multiply, you don't need the same name. So that means this 1 1 here not only can combine with the 3 1s, it can also combine with the 2 10s. In fact, every digit in one number can be combined with every digit in the other number. And our process of long multiplication is nothing more than an organized way of doing just that, making sure every digit in one number combines with every digit in the other. So we usually start with the last digit of the bottom number, 1 1 times 3 1s. Well, 1 times 3 is 3, but we also multiply the names. 1s times 1s is 1s. Well, then we do 1 1 times 2 10s. 1 times 2 is 2, but again, the names, 1s times 10s is 10s. So now we're done with the 1s. We move over to the 3 10s here. When we do that, what have we always been told we have to do down here? Either leave a space or put in a 0. Good. The reason we do that is because of this next step here. We do the 3 10s times 3 1s. 3 times 3 is 9, but we also multiply the names. 10s times 1s is 10s. Putting in that 0 is just making sure we line up the 10s with the other 10s. And then 3 10s times 2 10s. 3 times 2 is 6. 10s times 10s is hundreds. So then we go ahead and combine. We got 3 1s, 11 10s, so we carry the 1 to get 713. Now again, I realize after this first test, most of you are going to use the calculator for stuff like this. So I would hope that you're looking at this saying, okay, this is close to 20, this is close to 30, 20 times 30. I'm expecting an answer close to 600. 713 is a little bit bigger than that, but it's in the right ballpark. Because if you're anything like me, I have kind of fat, clumsy fingers. When I push buttons on my calculator, it's really easy to hit an extra button, and something like this can turn out to give me an answer of 5,613. Well, if I've looked at and done that estimate beforehand, I know right away that that's not correct. Division is the one operation that has been altered the most throughout the years. As we do division with not only whole numbers, but fractions and other forms of numbers, I'm going to show you a little bit of where the division process came from. To describe division, we have to go back a little bit and talk about the basics of multiplication. 5 times 3. If you think way back to like first grade or so, when you first started to multiply, before you memorized your multiplication tables and you knew that 5 times 3 was 15, how did you figure that out? Yeah, perfect. 5 plus 5 plus 5. You did repeated addition. Well, we have said, or I've said, that division is just the reverse of multiplication. So, since multiplication is repeated addition, 24 divided by 8 can be thought of as repeated subtraction. It's asking us how many times can I subtract 8 from 24? I subtract it once to get 16. Subtract it the second time, I get 8. Subtract it the third time, I'm at 0. So 24 divided by 8 is 3 because you can subtract 8 from 24 3 times. If you didn't end up at 0, of course, that's what our remainder is. So now with that in mind, let's look at a larger problem. Let's do 38,479 divided by 23. Now, I just said that division is repeated subtraction. I am not about to start subtracting 23 from 38,000. I don't have that kind of time. But if we could subtract large bundles of 23s all at once, we could do it rather quickly. And the way we do that is we look at the place value of the number we're dividing. This first digit is in the 10,000s place, so we're going to do 10,000 times 23 is 230,000. Can we subtract 230,000 from the 38,000? No, we can't. It's too large, so we cannot subtract the 23. We cannot subtract a bundle of 10,000 23s. So we go to the next place value, which would be 1,000 times 23, which is 23,000. Now that we can subtract. In fact, we can subtract it exactly once. Subtracting 23,000 gives us 15,479. So what we subtracted there was really 1,000 23s. So we just subtracted 23 1,000 times. Our next place value would be hundreds. 100 times 23 is 2,300. Oh, let's see. Will that go in there 7 times? No, it'll go in there 6 times, it looks like. So times 6 would be 0, 0, 18, 13. So it's 9, 7, 6. So 1,679. So again, what we did was we subtracted 6 bundles of 123s, or 100 times 6 makes 623s we just subtracted. Next place value is tens. 10 times 23 is 230. We can subtract that. Oh, can we go 7? We might be able to go 7. Let's try 7. Times 7 would be 0. 1 carry the 2. Yes, we can. We're left with 69. So again, we just subtracted 7 bundles of 10 23s, or 70 23s. And all that's left now is the 1s times 23s is just 23. And we can subtract that 3 times from 69. Leaves us with 0. So we just subtracted 3 more 23s. So what that's telling us is we just subtracted 23 1,673 times. So 38,479 divided by 23 is 1,673. Now you might be looking at that thinking, that doesn't look much like the long division I was taught. But it really does. If we look at what we've been taught to do, most of you are probably taught, okay, you start out with the 23. Does 23 go into 3? Well, no, it doesn't. So you leave it blank there. That's just this step here of checking, can I subtract 10,000 23s? Then we move to the next digit. 39. Does 23 go into 39? Yeah, it goes in there once. 9 was the last digit we use, so we put the 1 above the 9. 1 times 23 is 23, gives us 16. Now, if you look at this, if you look really close, you can see it's exactly what we just did here. Only, oops, this should have been 38 there, shouldn't it? Sorry about that. It should be 15. I wonder why it looked weird. It's exactly what we just did here, only we left the zeros off. So all this process of long division that we've been taught is just this whole idea of repeated subtraction that's just been shortened up to take less space and less time. Now again, I don't expect you're going to change how you do your long division. I just wanted to show that to you. The other thing I want to look at today, because it seems to be one of those topics that a lot of people struggle with, is integers. To deal with integers, we have to understand what the operation of addition really is. So we're going to set the names aside for now, and we're just going to work with the counts. We're going to work with the amounts. 5 plus 3, the technical definition of that. In fact, just defining the amounts 5 and 3 themselves are done on the number line. So here's 5, and here is 3. Numbers are represented by what we call vectors. All it is an arrow that starts at 0 and goes up to that number, or has the length of that number. Addition, or the operation of addition, is just taking those vectors and putting them together to make one solid vector, one continuous vector. So 5 plus 3 equals 8, because when you combine the vectors, you end up at 8. The total length is 8. So when we put in a negative number, like 5 plus a negative 3, the 5 is still there, but now we have to go the opposite direction for negative 3. Negative 3 looks like this. We're still going to combine the vectors, but now the negative 3 and the 5 work against each other, and we end up back down here at 2. Now, I don't expect that you're going to draw out a number line every time you add integers, but I keep that picture in the back of my mind. For example, let's say I have negative 14 plus 9. So here's 0. Negative 14 goes like this. Positive 9 goes the other direction, and it's shorter than 14, so it goes like this. This picture tells me two things. One, my answer ended up on the negative side of 0, so my answer is negative. Two, the arrows, the vectors, point in opposite directions. So the size of my answer, the absolute value of my answer, is the difference between 14 and 9, which is 5. So with bigger values, we might have 218 plus a negative 349. It's the same thing. Here's 0. Here's 218. Negative 349 goes the opposite direction, and it's going to be longer. So it goes to the negative side. And again, this picture tells me my result is going to be negative, and the vectors point in opposite directions, so it's going to be the difference between 349 and 218. So I'm just going to subtract them to get 131. So it's a negative 131. So I might have a negative 42 plus 71. So same thing. Here's 0, negative 42. Positive 71 goes the other direction, and it's going to be longer, putting us on the positive side of things. So it tells us our answer is positive. And again, the arrows are in opposite directions, so it's the difference between 42 and 71, which is 29. So it's positive 29. We might have a negative 43 plus a negative 19. There's 0, negative 43. Negative 19 goes the same direction. So it tells us this one's obviously negative, and since the arrows go in the same direction, it's just 43 plus 19. We combine the values to get a negative 62. So addition with our integers isn't too bad. Subtraction is where it really gets confusing. If you look at 8 minus 3, and we'll look at our number line again. If we were to draw a picture for 8 minus 3, most of us would draw a picture that looked like this. And of course it ends up at 5. We all knew 8 minus 3 is 5. But if we look at this picture, we realize that it looks an awful lot like 8 plus a negative 3. Because it is the picture for 8 plus a negative 3. Technically, if you get deep into mathematics, the operation of subtraction does not exist. The technical definition of this symbol here that we know as a subtraction symbol is add the opposite. So technically, subtracting 3 means add the opposite of 3. So add a negative 3. So 8 minus 3 literally does mean 8 plus a negative 3. Now, most of us have worked with subtraction enough that we can do 8 minus 3. We know what that is. But if we have other negatives in there, like negative 9 minus 7, changing it to subtraction helps. Or change it to addition, sorry, helps. So instead of negative 9 minus 7, we change it to negative 9 plus a negative 7. Now we can use our vectors. Negative 9, negative 7, that's going to be a negative 16. We might have 8 minus a negative 6. Now this is the one that most people usually find the most confusing. 8 minus a negative 6, we have to change that to plus the opposite. Well, plus the opposite of negative 6 is positive 6. So 8 minus a negative 6 becomes 8 plus 6, or 14. We can have negative 9 minus negative 13. Negative 9 doesn't change, but again, we're subtracting negative 13, meaning we're going to add the opposite. So plus the opposite of negative 13 is positive 13. So now it's addition. We got negative 9. Positive 13 is the other direction and a little bit longer. So the answer is positive, and it's the difference between 9 and 13, which is 4. Any questions? Okay. Well, multiplication and division with our integers is actually a little bit simpler. We go back to this. 5 times 3 we said was 5 plus 5 plus 5, just repeated addition. So negative 5 plus 3 is pretty simple. Negative 5 plus negative 5 plus negative 5. And of course that adds up to negative 15. And we've all been taught that a negative times a positive has to be a negative. And we can see why with the repeated addition. The one that's a little tougher to deal with, though, is 5 times a negative 3. Now this here, negative 5 times 3 is telling us you take negative 5 and you're going to take 3 of them and add it together. What this is technically telling us is you're going to take 5 and you're going to take negative 3 of them and add them together. Well, it doesn't make sense to take negative 3 of something and add them together. So what we do is we generally switch that around to be negative 3 times 5. And now it makes more sense. It's telling us you're going to take 5 negative 3s and add them together. And of course, that is a negative 15. The one that really breaks down with our definition of multiplication is this. Negative 5 times negative 3. We've all been taught, of course, that that has to be what? Positive 15. We've all been taught a negative times a negative is a positive. We've learned it and we've memorized it. But the question is why? I mean, technically, according to our definition of multiplication, this can't be done. We cannot take negative 3 of the negative 5s and add them together. We can't even switch it around. We can't take negative 5s of the negative 3s and add them together. So what we do to come up with the fact that that has to be positive is we look for a pattern. And this actually happens quite a bit in math, where our definition breaks down. So we have to look for a pattern, and we define our answer to be whatever makes that pattern continue. So if we're starting with a negative 5, negative 5 times 3 is negative 15. We've already seen that. Negative 5 times 2 is negative 10. Negative 5 times 1 is negative 5. If we look at this to find a pattern, whenever we start out with negative 5 here, if we take the number we're multiplying by, if we decrease it by 1, our answer actually increases by 5. Here it went from negative 15 up to negative 10. Here the number we multiply decreases by 1. We went from 2 down to 1. We went from a negative 10 up to negative 5. Let's see if that pattern continues. Negative 5 times 0 is 0. This decreased by 1. This went up by 5. So the pattern continues. So to keep going, negative 5 times negative 1, this went down by 1, so this has to go up by 5. It has to be a positive 5. Negative 5 times negative 2, well, that has to be a positive 10. and bring us to negative 5 times negative 3, which has to be 15. So the reason we define a negative times a negative to be a positive is simply because it continues our pattern. And we run into this a lot as well when we look at our powers. We'll come back to this, by the way, in just a second. You're defining powers. 8 to the third we know is just 8 times 8 times 8, which comes out to be 512. But how do we find 8 to the power of 0? Can anybody tell me what is 8 to the power of 0 without punching in your calculator? Okay, 1. Good. A lot of people want to say 0. Why is that 1? It's technically telling us to take 0 eighths and multiply them together. This is saying take 3 eighths and multiply them together. Well, we really can't take 0 eighths and multiply them together. But 8 to the power of 0 equals 1 because we look for a pattern again. 8 to the third is 512. 8 to the second power, or 8 squared, is 64. 8 to the power of 1 is 8. And it's the same type of thing as over here. When the power goes down by 1, the answer gets divided by 8. So now when we go from 1 down to 0 for our power, this has to be divided by 8 to give us 1. And then we can continue on into our negative powers. 8 to the negative 1, we have to divide by 8 again to get 1/8. 8 to the negative 2, 1/16. 8 to the negative 3, 1 over 500, oops, not 1/16, sorry, that should be 1/64 there. 8 to the negative 3 is 1 over 512. And you'll actually see a correlation between the positive and negative powers. They end up being reciprocals. 8 to the power of 2 is 64. 8 to the power of negative 2 is the reciprocal, or 1 over 64. Again, not because a negative power has much meaning. It really doesn't, but it's because it fits the pattern. Let's get back to multiplication of our negatives. So I'm going to have you guys yell out the answer for these. Negative 9 times 7 then has to be negative 63. Good. Negative times a positive is a negative. 9 times 7 is 63. 8 times negative 5 is going to be positive or negative? Negative 40. Good. Negative 11 times negative 7 will be positive 77. Good. A negative times a negative is a positive. So all that's left now for our integers, for our negatives, is to deal with division. Just like subtraction, division is not its own operation. To say 12 divided by 3 equals 4, the reason that is so is because 3 times 4 equals 12. So when we're asking 12 divided by 3 equals what that's asking us is, what do we multiply 3 by to get 12? So if we have 18 divided by a negative 2, what that's asking is, what do we multiply the negative 2 by to get 18? Well, 18 is positive, so the negative has to be multiplied by another negative, and it would be negative 9. So 18 divided by negative 2 has to be a negative 9. Just like with multiplication, a positive divided by a negative gives us a negative. Negative 36 divided by 4. Again, that's 4 times what number? Is going to give us negative 36. Well, 4 times 9 is 36, but it's a negative 36, so it has to be a negative 9 again. So negative 36 divided by 4 is a negative 9. Again, just like multiplication, a negative divided by a positive is a negative. Negative 40 divided by negative 8. Well, again, negative 8 times blank equals negative 40. What do you multiply negative 8 by to get negative 40? Well, it's going to be a positive, because negative times a positive is negative. Maybe 5. So just like multiplication, a negative divided by a negative gives us a positive. Any questions? So now let's get back to our powers with the negatives in them. Negative 9 squared. Negative 9 times negative 9, of course, will be 81. A negative times a negative is a positive. But the way I wrote it over here could cause some problems. If you punch it in your calculator like that, many of your calculators will give you an answer of negative 81, which is incorrect. Why is the calculator saying that? Because your calculator is doing 9 squared first and then applying the negative. In your calculator, to make this work correctly, you have to have parentheses around the negative. So when you punch it in like this, you get 81. Thing to remember, we're going to use squared on some of our formulas in this class. Anything to the power of 2 or anything squared has to be positive. So when you punch in your calculator, if it tries to tell you it's negative, you know you entered it incorrectly. So like a negative 7 squared has to be a positive 49. On this calculator, it works the same way. Negative 7 squared, it'll try to tell me it's negative 49, but really, it has to be positive. Let's look at some of the other powers. What if we have a negative 5 to the power of 3? Well, that'll be a negative 125. And it makes sense. If you think of it, that's 5 or 3 negative 5s multiplied together. Negative 5 times negative 5 is a positive 25. Times another negative 5 is a negative 125. So when it's to the third power, a negative number will give us a negative result because there are 3 negatives there. How about to the fourth power? Well, again, negative 3 times negative 3 is a positive 9. Times another negative is going to be a negative 27. Times another negative will be positive 81. So to the fourth power, there are 4 negatives. They cancel out, and we get a positive result. Of course, the pattern you've probably seen before is odd powers, it is possible to get a negative answer. Even powers, your result will always be positive. So negative 5 to the power of 6, we know before we even start that result is going to be positive. If you enter it in your calculator, you better get 15,625. On the other hand, though, negative 5 to the power of 5 will not be positive. It's an odd power, so since that's negative, it can be a negative result of 3,125. Any questions? Well, I know we have about 9 minutes left, but that's about all I have for the day. What I'm going to do is I'm going to give you the homework on whole numbers, pages 7 and 8, 1 through 59, the odds. Remember, the solutions are on Blackboard for those problems in that course information section. Then there's also some homework on decimals I'm going to give you, since decimals pretty much follow the same rules as whole numbers with the whole lining up the place values because of the names and stuff. And that's going to be on page 29 to 32, 1 through 91, the odds. Now again, I realize there's a lot of problems there. I don't expect you to do all of them. Remember, we don't turn in the homework in this class. If you do the first few and they seem really easy, skip ahead. I know these first few assignments are going to be extremely easy for you guys. So don't waste your time doing stuff you already know. I would highly recommend that if there are any word problems, you take a good look at those. Because on our tests, especially after this first unit, we tend to lean as heavily as we can on word problems. So at least make sure you look at the more difficult ones at the end of each assignment. Okay, with that, I'm going to call her a day.